Hello. In this video we're going to be looking at three things. We're going to be looking at three types of radiation: how they travel, how they penetrate materials, and how they ionise materials. Radioactive materials are radioactive because they actually have an imbalance, or they're unstable. This is due to the number of neutrons and the number of protons in the nucleus being unbalanced. If we have a look here, we can see in common elements like hydrogen and helium that we actually have one proton and, in this case, one neutron. Here we have two protons, and of course two of these four must be protons, so the other two must be neutrons. And again down here we've got 6 protons and 6 neutrons. If we were to plot a graph of the protons versus neutrons, we end up with this one-to-one relationship, or a directly proportional line. However, if we look a little bit further on, what we find is, rather than continuing on in this straight line, actually the elements don't plot like that. What we find is they start to diverge and they start to move away from that line. Now, they're actually scattered slightly either side of this new black line here. Now, this new black line is actually elements that are stable, or the line of stability. Okay. So what we find is that when we get to the heavier elements, when we start to get up to, for example, elements such as here gallium or germanium, which have in this case 31 protons, and they certainly don't have 31 neutrons. Here again 32 protons, they don't have 32 neutrons. And obviously we could go down to some of the heavier ones. So let us take a look at something like mercury, which has 80 protons. We'll be expecting 160 nucleons, so that's protons and neutrons, but we don't have 160, we have over 200. So we find that the line of stability moves up here. What we find though is that when elements move either side of this line of stability, they become unstable and they start to give off radiation. And that's the purpose of this session. I'd like you to watch this short video, because this short video explains to you the three types of radiation: alpha, beta and gamma, and also explains to you how they are affecting materials, how they travel, how they penetrate, and how they ionise materials.
Their potential into the organs. The beta radiation consists of electrons or positrons, which compared to alpha particles have a much lower mass. Therefore, the range in the air is up to a few meters. They can also penetrate deeper into the skin and emit their energy there. Also, through ingestion of a beta emitter into the body, for example, there could be circumstances which may lead to severe radiation exposures into the body. Thankfully, beta radiations can, for example, be shielded by a few centimeters of plexiglass. However, the process of shielding may produce X-rays. This could then, in turn, be intercepted by panels made from a heavy metal. The gamma rays are photons. They permeate matter easily and ionizes the surrounding atoms as it passes through matter. Gamma rays cannot be shielded against completely. However, the intensity can be reduced by several centimeters of thick lead plates. Exactly how the various types of radiation affect biological tissue and how dangerous they are depends on many different
how they ionise materials. Hopefully you noted that alpha, beta and gamma travel different distances, and they're stopped more or less easily, and they have different ionising abilities. This second video reinforces some of those ideas from the first video, but actually gives you a little bit more detail and also shows you perhaps what you might see if you were to do a practical demonstration.
Hi there, I wanted to do a quick demonstration to show the three common types of ionizing radiation: alpha radiation, beta radiation, and gamma radiation. And to do that, I've got a simple Ludlum Model 3 survey meter with a Ludlum Model 44-9 Pancake GM detector attached. This type of detector has a thin mica window that allows alpha, beta, and gamma radiation all three to penetrate, so I can demonstrate all of them. So to start out with, I'll turn the audio on. I'm on the most sensitive scale, which is the 0.01 scale. You can hear the natural background radiation there. As I approach with this polonium-210 alpha source, alpha travels a very short distance, maybe a couple of centimeters, an inch or two in air. So you can see I've got to get really close, within an inch, before I can even detect that alpha radiation. If I hit the reset button here, I'll show it again. I've got to get right up on that detector before it starts to see that alpha particulate radiation. To demonstrate how easy it is to stop alpha, I've got a single sheet of paper that I'll slide in between the detector and the source, and you can see it takes a minute for that to fall back down to 0, but it's very easy to block out alpha radiation. Alpha is primarily an internal hazard. If you ingest or inhale material that emits alpha radiation, it comes in close contact with your body tissue and can cause harm that way. Outside the body, it's pretty harmless. It can't even penetrate the dead layer of skin cells on our body. To demonstrate beta radiation, I've got a beta source here, and you can see already several inches away it's giving me a reading, so I'm going to range up to the times 1 scale here and hit the reset button. But obviously the betas will travel farther than the alpha. I'm going to set that there. I'm going to grab my piece of paper and stick in here, and you can see that the paper doesn't do anything really to block that beta radiation. But something like a sheet of plexiglass, if I stick that in between there, that'll block it down and send it right back down to essentially background. So it's pretty easy to stop beta radiation. It'll travel maybe 10 to 20 feet in air depending on the energy of the beta radiation or the source that you've got. The last type of radiation I want to show is gamma radiation. I've got a cobalt 60 button source here, and it's not a real strong source, so I can't show you the distance that gamma is capable of traveling. If you have a strong source, these guys could travel hundreds of feet in air. But you can see here that what I can show you is the penetrating ability of this type of radiation. I can take again that piece of paper and stick in there, and it's not going to do anything at all. If I take the plexiglass and put in there, again, that blocked the beta radiation, that doesn't do anything. It really doesn't block it out at all. What we need to shield out the gamma radiation is dense material like lead, concrete, steel, things like that. If I put the lead, I've got some lead here that's wrapped in tape. I'll take a couple sheets of that and slide in there. Then I can range it back down to that times 0.1 scale. And you can see that was pretty effective in blocking out that gamma radiation. But gamma is very penetrating. I can put my hand here and it'll penetrate right through my hand. In fact, it will penetrate through the back, the metal back of the detector. So gamma is the one that's most penetrating. We typically use time.
Okay, so there's 3 main things we have to take from this video, and it's quite important that we understand these 3 main things because they might seem at first slightly counterintuitive. That means not what we would expect. So what we've got here is I'm going to try and show you the 3 key things you need to pick from that video and the one before. We need to look at the distance that they travel for alpha, beta and gamma. We need to look at the penetration potential. That means the ability to penetrate or burrow into a material. And also we want to look at the ionization potential. And if you recall, that's where we're knocking electrons off, we're creating ions, and of course they can then lead to mutations and cancer. So when we think about the distance travelled, if you remember, the alpha particle really would have come in 3rd place. It didn't travel very far. And also the beta particle travelled quite a long way. Remember, that was the electron, that could go quite a distance, but it was nowhere near as far as the gamma. And remember, the gamma wasn't a particle, but it was a wave. Just a little bit about the notation. Sometimes you'll see alpha written as a fancy A. In fact, that's actually the Greek letter alpha rather than A. You'll also see beta. Again, it looks like a B with a tail on it, and that is the Greek letter beta. And you'll see gamma, which looks a bit like, again, a fancy Y, and that is gamma. So remember, particle, particle, wave. And let's look at penetration potential. You probably noticed in there that alpha really didn't go very far. Alpha only travelled a few centimetres in air. In fact, it was stopped by things like skin, it was stopped by your clothes, a simple bit of paper. So outside your body, alpha's really quite safe because it's stopped by things like your skin and your clothes. Beta, however, is a little bit more dangerous because beta can make its way through the top layers of your skin and start to get into some of your cells. So, of course, it has then the potential that it could actually damage you through ionisation. Gamma, that penetration potential is massive. Remember, gamma can pass all the way through you. But that's quite important when we look at this last concept, because if gamma can pass all the way through you, the chances that it will ionise are actually very, very low. And that means its ionisation potential, i.e. its potential to cause ionisation, is actually very, very low. So it would come in third place. Beta, if you remember, travel quite a long way. It can actually penetrate quite a long way, and it also is quite good at ionisation. So it's really not something you want to get too close to, because it's quite difficult to stop with just what you're wearing and your normal clothes. And if it does get into your body, it can cause some damage. Alpha. Now, alpha, yeah, it doesn't penetrate very far. It gets stopped by your clothes. It doesn't travel very far, so you've only got to go a few metres away from the source, and you're safe. But should something happen, and maybe you swallow it by mistake, I don't know, maybe it's in some food, maybe someone's poisoned your food or something, if you were to swallow the alpha radiation, or it to get inside your body, it has a huge ionisation potential. It's really difficult. It's likely to cause you significant damage. Okay, so finally, let's try and explain what we've been seeing there. So one way we can think about alpha radiation is we can try and think about alpha as being a bit like a bowling ball. Love my little diagram of a bowling ball. Now, bowling balls don't go very far. Now, one of the things that kind of sort of analogizes or links to in our mind is that alpha doesn't travel very far in air. So bowling balls, if I tried to throw a bowling ball at you, if you stood a few metres away, almost certainly you'd be safe. However, if it did hit you, ouch, it's going to hurt. It's going to cause you quite a lot of damage. In the same way, if alpha were to hit one of your cells, it's got a very good chance that it could damage a cell. Remember, it's a large thing. Remember, it's a helium nucleus. Okay, so it's a helium nucleus without the electrons whizzing around it. It's got a big chance of hitting you, likely to cause damage. Beta, you can imagine a bit like a tennis ball. Again, bit of a poor drawing, but I'm sure you can imagine that as a tennis ball. Tennis balls, of course, they travel further. If you get a tennis ball, I'm pretty sure that all of you guys could throw a tennis ball a little bit farther or further than you would do with a bowling ball. Again, though, if it hit you, it's likely to cause a little bit of pain, so it's going to be kind of a little ouch this time. It's not going to be so bad as getting hit by a bowling ball. Maybe it might sting a little bit, get a bit bruising, but you're unlikely to break any bones. And again, the same thing here. Beta is unlikely to do too much damage because it's unlikely to actually hit anything inside a cell because it's so small. And the last thing then is we've got the gamma radiation at the bottom. And that's a bit like a wave machine at your theme park or your beach or something. It travels a long way. Oops, can't write long there, so long way. But the thing with travelling so far is that actually it's very, very difficult to stop. You can't really avoid it. So there's no point really worrying too much about gamma radiation because likelihood is it's going to pass straight through. It's unlikely to actually cause damage because if you remember, the ionisation potential is low. That means it's unlikely to cause ionisation. So hopefully in this video you've got the three things we started off with. Let's just remind you. Here we go. So we've got the three types of radiation, how they travel, how they penetrate materials, and how they ionise materials. Thank you for listening.